Okay, chapter 4 is about microscopy and staining and using that information ultimately for classification. So we're going to discuss different types of microscopy and different staining techniques, mainly because these are tools we use to identify and classify microorganisms. And in terms of medical applications, you would want to then be able to correctly and quickly identify a microorganism so that you can come up with an appropriate treatment, for example. So there's fundamentally two types of microscopy. The one we're using in lab is using a light microscope. Sometimes we call it bright field microscopy using the compound light microscope. We also have an electron microscope. We do have one on campus. These are very expensive and much larger than the desktop light microscopes that we use. Light microscopes cannot achieve a resolution more than about 200 nanometers. And we will talk about what resolution means, resolving power. But they can't resolve any structure more than anything smaller than 200 nanometers. And so you really need, for some structures and for some entire organisms, you need electron microscopes to be able to visualize very, very small structures. So magnification can get up to 100,000x. With our light microscopes, we can usually achieve, in the ones we have here for students, about 1,000x. And so you get a much better, much bigger magnification and much better resolution. So you can look at bacteria, viruses, small structures, and then even molecules and, to some extent, large atoms. Of course, we're not going to go to that point. We're going to be looking at cells, viruses, and maybe some structures within or outside of those cells or viruses. The two fundamental types of electron microscopes are transmission electron microscopes and photographs of images created with transmission electron microscopes are called transmission electron micrographs. So TEM would indicate a photograph made with that kind of microscope. And a scanning electron microscope, SEM, produces a somewhat different image that can be shown. So when you see SEM and TEM on an image, it's telling you the type of microscopy that was used to generate the image. Electron microscopes always make black and white images, but then they can be colorized artificially to give some, to make them a little more attractive. And this picture just shows, on the left, you see upside down, if your eye is at the very bottom of this picture, your eye would be at the bottom looking through the eyepiece. The light comes from the lamp at the bottom of the microscope through a condenser lens, through the specimen, then through the objective, and then through the eyepiece to your eye. In an electron microscope, your eye is not directly involved at all. In other words, you don't stick your head into the beam of electrons, because it's not a beam of light, it's a beam of electrons that's passing through various magnets that focuses the beam of electrons. It passes through the specimen, and then it ultimately lands on a detector screen on the far end of the microscope, and you can get then an image. But you have to look at the image on a monitor. You don't put your eye directly into the beam of electrons. Shown in letter B is what it might look like in a lab. You can see how big it is, and then you can see the monitor next to it. And then shown in C is a transmission electron micrograph showing some cells. So if you have a scanning electron microscope, the difference between scanning and transmission is the scanning electron microscope only can look at the surface of objects. the external surfaces, it creates these very three-dimensional images. And like I said, they would initially be black and white, but then somebody has colorized these. Whereas a transmission electron micrograph would be more like this one here. A transmission electron microscope creates the image as if the object has been sliced through. But in fact, the object has not been sliced through. It's whole or intact, but the way that the electrons pass through the specimen creates an image that looks very two-dimensional, but you can see what's inside of a cell using a TEM. When you use SEM, you can only see the surface structures. So they'll be used for different purposes. This is a compound light microscope, bright field, and certainly you should still be familiar with the ocular or eyepiece is where you look through. That typically has about a 10x lens in it. Then the objective lenses of different magnification strengths, all connected to what we call the rotating nose piece. The stage is that black surface. The stage clip is where you put the slide. Underneath the stage, there is a called the iris diaphragm. It is a little lever somewhere located, depends on the design of the scope, but some kind of lever you'll find under the stage that can either allow more light or less light in through the specimen. Then you have the coarse focus or coarse adjustment knob and fine focus. Okay, so basic parts of a microscope. When light hits the glass of the lens, for example, it will bend. So the lenses that we use in our microscopes are called convex lenses, and it bends the light. And the reason that has any importance at all is simply that when you look at a specimen under a compound light microscope, the image you see is completely inverted, not only top to bottom, but also left to right. And so you'll notice when you're using a microscope, as you move the slide around, when you feel like you're moving the slide away from you, the image you see through the eyepiece seems like it's moving towards you. When you think you're moving the slide to the left, the image you see seems to be moving it to the right, and so on. And that's because of that complete reversal of the image because of the way the light passes through the lenses. So this, within the bright field microscope, this is really the kind of microscope. I mean, if we classified the kind of microscope that Leeuwenhoek used, we would call it a bright field microscope. It was a simple microscope because they only had one lens. And then our microscopes have two lenses. So at least two lenses that the image passes through, the objective lens and the ocular lens. And we can get up to about 1,000x total magnification with these scopes. All right. Our microscopes that we have in lab can also switch to what we call dark field. So there is a selection, kind of a setting that you can select for dark field. On our scopes, it says DF for dark field. And dark field is sometimes better. It just makes a black background instead of a bright white background. So for some objects that gives you better contrast, you can see better. And then we also have phase. And you can use phase for, that's pretty good for specimens where you are not going to be able to stain the specimen. Like if you want to see something actually swimming with its flagellum, you can't fix and stain that item because then it would kill it. So when you have live specimens, sometimes you use phase, but honestly, you use whatever setting gives you the best visual of the object. So these are just options that you have. In this picture, bright field is the one you may be the most familiar with. I mean, there's a lot of light coming to the eye. Typically, we have to cut back on some of the light. This would be a cheek cell with some bacteria on top of it. In dark field, you can see it makes the background very dark. So certain parts of the image are showing up maybe better. And then in phase, you get kind of this, it depends on which phase setting there are different phase settings you can choose, but by switching through, sometimes you'll get a better image. And it has to do with filters that are put into place to give different images. So phase contrast, we will play around with that a little bit in lab. We don't have the Nomarski, so I won't mention that one. So A, B, and C are ones that we will be looking at in our lab. When you go to 100x on our microscopes or on virtually any light compound microscope, you want to use oil. That's why they're called the oil immersion lens. And the oil immersion lens is designed to use oil. In other words, if you don't use oil on the oil immersion lens, you get an effect that's shown on the left side, part A of this image. So you see that there is, because there's no oil between the cover slip and the objective, the light, remember the light bends because of the glass, and even in a glass cover slip, it's gonna spread out after it passes through the glass. And so the oil will actually straighten out the beam of light. So you get more light going straight through the objective. And so more light is gonna really matter in being able to see the very small objects you're going to be looking for under the 100x objective. So it just, the oil just minimizes what we call the refraction of light, meaning the bending and therefore the waste, some of the light leaving, not passing through the objective. So the oil will correct for that refraction. So this picture, you don't have to memorize any of this, but look here at the bottom, towards the bottom here, you can see with no microscope, the unaided eye, you can see pretty well in what we call resolution or resolving power, like the size of the objects you can see clearly. Transmission electron microscope and scanning electron microscope get you much, much further into smaller and smaller objects being able to be seen clearly with good resolution. The compound light microscope gets you, to a reasonable point, but it's not as good as the electron microscopes. We're not going to talk about the scanning tunneling microscope, and we're not going to talk about the atomic force microscope. So the others here, you can see kind of how they compare. An electron microscope costs a lot of money, so we're in the hundreds of thousands of dollars range. So that's why you typically won't see those in a student lab. And like I said, we have one on our campus, but it has to be shared. And that's pretty typical for a piece of equipment that expensive. Okay, so in the next lecture segment, I'm going to explain the concept of resolution or resolving power. I think we'll start with that on the next lecture segment.